So my name is Dick Dubielzig. I have been here at the University of Wisconsin since 1983. Madison is my hometown, so I came back here to be a part of the veterinary school as soon as it was opened. Uh, I'm an anatomic pathologist, and I'll explain a little bit of what that means. The lab that I work out of is called the Comparative Ocular Pathology Lab. This is our logo. And an anatomic pathologist is more or less self-described. We study pathology is the study of disease, and we study disease based on a vast knowledge that we've acquired in our training to learn about anatomy, and that includes both gross anatomy. If you were doing autopsies, for instance, that would be how you'd begin with a pathology, or what we do in our lab is we receive eyeballs in the mail, and then we study them both from gross perspective, and also this image of our logo here shows a slide tray, and these are eyes that are cut in such a way that you can examine them under the microscope. So an awful lot of what we do in our lab is studying the anatomy of eyes under the microscope. And most of what we do is studying the anatomy of the pathology of eye diseases. But we've always encouraged zoos and aquariums and people who have access to what we call exotic animals across the spectrum to send even normal eyes. And since I retired in 2014, my passion has been to put together the study of the anatomy of a wide variety of different types of animals. So that's more or less what I'm going to share here. Dr. Moat talked mostly about the retina, and I'm going to concentrate on different adaptations in the anatomy of the retina based on the lifestyle or the lived experience of different types of animals. So this is just an image of what we would see as an anatomic pathology studying the retina. I don't have any expectations that you're going to memorize all the anatomic details here, but I do think it would be good for you to appreciate that the retina is a very complicated and very beautiful structure. The things that I'm going to talk about basically have to do with just a few areas of the retina. I will, can you see that? I will spend some time talking about the ganglion cells. So this would be the front of the eye up here. Light would come in from the front and traverse through the retina. The retina is transparent, so light can easily pass through it. So in the inner aspect of the retina, we have the ganglion cell layer. Ganglion cells are the nerve cells that send an image to the brain. So they have an awful lot to do with the function of the retina. The other, we're going to skip then all the way to the back, and these are the photoreceptors. You might know them as the rods and cones, and that is the layer of the retina where light actually interacts with tissue to form a neurosensory impulse. And then one other area, this is the tapetum lucidum, which Dr. Moat described. It's that birefringent, it's that reflective area in the back of the eye that allows animals that have one to perceive vision a little bit better in dim light situations than if they didn't have a tapetum lucidum. So the first thing we're going to talk about is vision in dim light and what are the differences. You can read the bullet points here, but I'm going to just go dive right into the morphology. This is an image from a fantastic book that describes comparative anatomy by A.G. Walls, and it shows a series of nocturnal animals and what their eye looks like, arrhythmic, which Arrhythmic means that these are animals that specialize in being out at dawn and dusk. So it's kind of in between, not completely nocturnal, not completely diurnal or daylight vision. And then these are animals that are adjusted to be out in the daytime. It's no coincidence that all the nocturnal and all the arrhythmic eyes are from mammals, and that more typical diurnal eyes are either birds or reptiles. Paleontologists tell us that way back in time, hundreds of millions of years ago, there's suspicion that mammals were already warm-blooded, which means that they could take advantage of the nocturnal niche, whereas reptiles back in that same time are cold-blooded, which means that they need to be in the bright light in order to kickstart their metabolism. So it's no surprising, going way back in time, that birds and reptiles tend to have eyes that are adjusted for high visual acuity in a bright light environment, whereas mammals tend to have eyes that are good for nocturnal vision or dawn and dusk type vision. Now, and this is all accentuated by the period of time when mammals had to coexist with dinosaurs. Their nocturnality was probably even more accentuated. So those that survived the dinosaur era tended to remain dim light specialists, except that now the predatory dinosaurs are gone, and some mammals like humans or like primates could readapt to be largely diurnal or visual acuity specialists. Looking at the retina, the animals that see in the daytime with a high degree of visual acuity tend to have more cones. You can see the conical photoreceptors here are the cones. The cones take up more space in the retina. Therefore, this layer is the nucleus of the rods and cones. So there are equal number of rods and cones as there are nuclei in this what's called the outer nuclear layer. And then they tend to have lots and lots of ganglion cells because they're specializing in visual acuity. Ganglion cells send the information to the brain, so they're going to have more ganglion cells. The goal here is to have one cone send its images to one ganglion cell. That's a ideal. It's not often achieved. Whereas the nocturnal eye will have lots and lots of rods. Rods are the photoreceptors that are responsible for vision in dim light. They do not see things like color, and they do not provide a whole lot of visual acuity. So, but they take up much less space, as this graphic shows. So in a nocturnal animal, there's likely to be more ganglions, more nuclei in the outer nuclear layer, and fewer ganglion cells. So let's look at a real life situation. Here's a couple of eyes. These are both from cats. The eye on the left is from a leopard cat, which is sometimes also known as a fishing cat, and it's an exquisitely nocturnal hunter, adapted for vision in the dark nighttime. And the cheetah is a vision hunter. It hunts in the daytime, and it's largely diurnal vision and eyes that are adapted for that. So let's look at this from the chart. You see that it has I call it a wraparound or a picture window cornea. The goal here is to let as much light in as possible, just as you'd open up the aperture in a camera when you're taking dim light photographs. The lens, it tends to be closer to the center of the eye. It tends to be rounder as compared to the diurnal animal. The goal here is to take in as much light as possible, and then the lens will focus that light into a small area of the retina So let's say if you're existing on starlight, there may be just a few photons, but in order for those few photons to form a useful image, the optics of the eye will concentrate the light in a small area of the retina. So that's the goal of a nocturnal eye. The diurnal eye is sort of opposite. They function in bright light. They don't have to worry about concentrating the light. So they have a small cornea, and then they have a lens which is flatter and moved forward in the eye. And the goal here is to project an in-focus image in a large area of the retina. I think of that as being more pixels for the ganglion cells to work with to give a better visual acuity. So that's real life. Here's another example. These are among the squirrels. And on the left is a flying squirrel, which is a exquisitely nocturnal squirrel. You won't see them. They're all over the place here, but you won't see them because they're out only at nighttime. And again, I don't have a great gross picture, but you can see the cornea up here is what I call a picture window cornea. The lens is large toward the center of the eye and round. And here's the back of the retina. You can see all these nuclei in the outer nuclear layer. Whereas the ground squirrel, the ground squirrel comes out in the daytime. It forages. Let's just take an example. It forages on the prairie, and it has to worry about predation from above. So it needs not only to be able to focus in the bright light, it also has to look at the super bright light in order to surveil for danger. So here's the retina. Here is the outer nuclear layer, and the photoreceptors are largely cones. It was thought for a while that the ground squirrel had a pure cone retina, but that doesn't seem to be true. It's commonly used in vision research for just that reason. You might be struck by the yellow color of the lens, and a number of animals who have vision in bright light have a yellow lens to protect against UV light damage. Dr. Moen talked quite a bit about eye shine, or the tapetum. I will try and skip through this rather quickly because I have some of the same points to make. You're probably familiar with this phenomenon of eye shine. If you shine a flashlight in the dark at most of our common domestic animals, you'll see this eerie phenomenon of eye shine. If you do the same thing in a person, or if you take a flash photograph of a person, you'll get eye shine too, but it'll be red rather than this bright white. And that's simply because the light, in fact, reflects off the back of the eye, even though there's no tapetum. Dr. Moant showed this. This is what the ophthalmologist sees when they look in the back of the eye. This beautiful image of the tapetum lucidum. The tapetum in virtually all the animals that we deal with is always on the upper side of the eye, and I think the reason for that is if you think of an animal standing on a rock in either dawn or dusk and looking off into the horizon. There's going to be a bright field above, and there's going to be a dark field below. And that lower dark field is perused by the upper part of the retina, and that bright field above is perused by the lower part of the retina. So it makes sense that the tapetum would be on the upper side. If you take either whales or seals, they dive deep in the water and they need to have vision in dim light with no horizon. They have a tapetum that covers the whole back of the eye. So this is a little phylogeny. The animals that we deal with as veterinarians are largely, of course, we have all sorts of different animals that don't fall into these groups, but they largely fall into the carnivora, your dogs, cats, bears, weasels, skunks, etc., and your ungulates, your hooved animals. And I've just chosen the even-toed ungulates, so this is a representative of the ungulates. These are the ones that do have a tapetum. These are the ones that don't have a tapetum. And all of the animals that don't have a tapetum are not so much dim light animals that live in dim light, but animals that have adapted for bright light circumstances. Same among the carnivores. We can break them up into two different types. Those that are related to dogs down here. And I apologize that you really can't read the writing here, but these are all dogs, bears, weasels, etc. And then those that are related to cats on the top here. And the ones that don't have a tapetum are your mongoose and meerkats, which are both adapted for to be diurnal daytime hunters, and they apparently seemingly lost their tapetum. Tapetum lucidum is pretty common among fish. Just a couple of examples here. This is a sturgeon, a very ancient fish, and the tapetum is in back of the photoreceptors where you would expect it to be. And in fish, mostly the reflective tapetum is made up of the amino acid guanine. And guanine can exist all over the fish. Any fish that has a silvery appearance to its body, that silverness is based on the fact that there's guanine in the skin. So not surprising that there should be guanine to cause a reflective layer in the retina as well. This is an arowana, which is an interesting fish. This fish lives in murky waters, and it hunts both above the water and below the water. But anyway, you can see, again, a guanine tapetum interdigitating with the outer portion of the retina. Raisin sharks have a very interesting tapetum, and it's adjustable. If the animal is swimming in bright light close to the surface, the cells of the choroid where the tapetum is will be positioned so that they are perpendicular to the retina. Whereas if you go to deep light where they have dim light, those cells will lay flat in the back of the retina. And this is a guanine tapetum too. You can tell that if you look now with polarized light, with intense polarized light at these same eyes, you'll see the position of the guanine deposited on these columns or stretched across the back of the eye. In bright light, the guanine is not positioned in such a way that it will provide a highly functional reflective surface, whereas in dim light, the eyes will have eye shine as they would in other types of animals, Okay. Now we're going to switch to vision in bright light to optimize visual acuity. And here's two examples. This is a red-tailed hawk eye, and this is a cynomolgus macaque eye, a primate. Among the mammals, the primates are the kings of visual acuity, and they're the most adapted for lifestyle, which takes advantage of bright light in a diurnal environment. So this is a monkey eye. You can think of it as being a human eye. There's very little difference between the two. But we talked about this a little bit. They have a relatively small cornea, a relatively flat lens, which is pushed way far forward in the eye to have a large image projected on the retina. And then they have a specialized area of the retina. This is the fovea, the macula, and the fovea. Here's the optic nerve in this monkey eye. So when you're looking directly at something, you're focusing light on your macula or on your fovea, and that's when you have the best visual acuity. Same thing in the hawk. I'll talk a little bit about their fovea in a little bit. You might be wondering what's this radiator-like structure sticking up into the eye, and this is the pecten oculi. It's a highly vascular structure. The retina itself has no blood vessels, and so the blood from the blood elements from the pecten oculi diffuse across this empty space here called the vitreous and help to nourish the inner portion of the retina. The outer portion of the retina, where the photoreceptors are the most highly oxygen-dependent cells in the body, and they have a blood supply in the choroid that's the most heavily perfused capillary bed in the body, but I'm not going to spend a lot of time looking at that. So here's this now is a orangutan. Basically, it's the same as that cynomolgus monkey, or it's the same as a human eye, and the arrow is pointing to the fovea. Notice the fovea is directly in the center of the eye as you look forward. And then we like to look on microscopic image, and this is a cynomolgus monkey, and this is a chimpanzee. Here's the optic nerve, and here's the optic nerve. So here a little bit temporally on the lateral side of the optic nerve in the midline plane, you'll have the fovea. I told you you can tell, if you look at the retina, you can tell whether it's important for visual acuity by looking at the number of ganglion cells, and look at all the ganglion cells that are near the fovea in these two images. This is the dog retina. Once again, Dr. Moat showed you an image of where the area centralis is, the portion of the dog retina that's most useful for visual acuity. Well, this is what it looks like to the pathologist. And now what we're seeing is a much higher number of ganglion cells than I showed you in that first image of a dog retina. Moving towards what you would see in a fovea, but not nearly as advanced. Notice that there's still lots and lots of photoreceptor nuclei. There's still lots and lots of rods versus cones, unlike you would see it in the primate eye. This is, we're going to human now. This is a medical image of the fovea as your ophthalmologist might see it. This is a heat map showing numbers of ganglion cells, and you can see that there's a tight circle around where the fovea would be. This is a technique called a multifocal electroretinogram, which allows you to measure the electrical activity of the retina in a myriad number of little localized areas of the retina. And this image, this map, simply shows the amplitude of the electrical response. You can put that into your imagination and try to imagine what that actually means. But pretty clearly, it shows that the area of the fovea has a amplified electrical response. I suppose not surprisingly. Many birds have a fovea. And I wouldn't be able to name this bird or that bird or what have you, but lots and lots of birds will have a fovea or a very advanced area centralis. The point I want to make here is that some birds have not one but two fovea per eye, and this includes all of the diurnal, all of the daytime hunting birds of prey. And this is a microscopic image from a kestrel, and Dr. Saukup and Pot have created this wonderful ability to take a histologic picture, a microscopic picture, which includes both fovea, and this particular one is a kestrel. They have studied birds of prey, and you can see they're broken up into a temporal fovea and a nasal fovea. The temporal fovea is situated in such a way that when a bird is looking directly at you, it's using that temporal fovea in both eyes. So Dr. Moat talked about the stereoscopic advantage of seeing with both eyes to measure depth perception, whereas the nasal fovea is independent for each eye. And if you watch a bird, you'll see that sometimes it'll eyeball something using just one eye, and that's when it would be using that nasal fovea. Doctors Chris Murphy, Jim Verhoeven, and Mike Nork got their hands on a red-tailed hawk and developed a technique for doing a multifocal ERG on a red-tailed hawk with two fovea. And exactly what all this means is hard to imagine. But if you use your imagination, you can see the amplitude, the amplitude of the electrical activity is much more widespread over the retina, which I think is a pretty astounding image. This is what we call a plastic section of a falcon retina. These are the rods and cones. These are mostly cones. The rods are these long outer segments here. And what I want to show you here is in the cones, immediately adjacent to where the light is absorbed. That's this little conical area at the end of the cones is an oil droplet. If you take that retina, this is from a chicken, and you just simply take a chicken eye, open it up, scoop out the retina, flatten that retina on a microscope slide, and do nothing else other than look at it with a microscope slide, perhaps enhancing the color a little bit. You'll see these gorgeous oil droplets. And whereas mammals have two color variant cones, basically green and blue, whereas birds have four, which includes a cone that's devoted to ultraviolet light. So they have much enhanced color vision, even more so enhanced because they have this filter right in front of where light is absorbed in the photoreceptors that only lets the appropriate wavelength of light into that photoreceptors. I don't know what it would take to actually try and determine what exactly birds see when they're looking at color, but that would be a great thing to investigate. This is a iguana eye, and it's I put it on here to show that it has most of the features that we see in bird eyes are also seen in many types of reptiles, particularly the lizards. This image shows the fovea here. This is analogous to the pectinoculi. It's called the conus papillaris, but it's a vascular structure. And then there's other similarities between reptile eyes and bird's eyes. You probably know from popular science that birds are in fact reptiles. They are directly descendant from theropod dinosaurs. So they're phylogically speaking, birds are reptiles, full stop. This is a chameleon, has interesting vision. Chameleon has only a very small cornea, and basically the whole retina is nothing more than just one big fovea. And here's another view. Eye opened up. Here's the yellow around the fovea, the macula lutea, you could call it, and the retina doesn't extend very far beyond the fovea. Here you can see in cut section. Here's the fovea. There isn't that much retina beyond that. So the chameleon has excellent visual acuity, but very little visual field. It has a remarkable tunnel vision. Now the chameleon is both predator and prey, and so it needs to be aware of what's going on around it. And if you've ever watched videos of chameleons, their eyes function independently and they're constantly looking in different directions. And that is to make up for the fact that they don't have wraparound vision like Dr. Moat showed you in mammals, but they have a very high degree of visual acuity. I've never tried to catch an insect with my tongue, but that's what they do for a living. And I think you need to have good vision and good depth perception. Okay, we're going to talk a little bit about vision in very bright light. I showed you some images of ground squirrels. This is what's important to a ground squirrel. Again, we have the yellow lens, and they have a retina that's very rich in cones, but it also has the outer portions of the cones are embedded in this pigmented layer, the retinal pigment. It's called the retinal pigment epithelium. Here's an electron microscope. Here's the outer segment, and here's that pigment that shades the outer segments. And I think that's an adaptation to allow it to maintain vision under extremely bright circumstances. And then there's another animals that need to have vision in bright light will often have something that takes the form of a baseball hat. They'll have a shading apparatus that will cut down the amount of glare from the bright light where they spend their days. Most probably advanced in the camels and llamas, also a camel, but we see it in horses and we see it in a lot of grazing hoof stock that live on the prairie where they don't have access to shade and they can't escape the bright light. I'll entertain questions if you have them.